here's an example of the conjugate roots theorem. 1 plus 2i is a root of this quadratic equation. Now, in complex numbers, as you know, we use the letter z to denote the variable, but of course it doesn't matter. We could have called it x. We could have written this as x squared minus 2x plus 5 equals 0. Anyway, this is true. It's also true that z bar, that is the conjugate of this root, is also a solution of this equation. Now you could go and get the roots of this directly by writing down what a, b and c are for this quadratic equation, subbing in, and you'll see straight away that you get two solutions. From the plus or minus square root part, the plus or minus actually leads to the two different solutions, the conjugate pair. Now we can also prove that this is true from the previous video, from the properties of the conjugate of a complex number. So we can start by plugging in 1 plus 2i for z. So that's what I've done here. We know that that's going to equal 0. Now the left hand side of this is a complex number. Well, we know it's actually 0, but we can pretend we don't know what it is. We can get the conjugate of the left hand side of this equation. But if we get the conjugate of the left hand side, we have to get the conjugate of the right hand side. So we have a complex number on either side of this equation. Actually, the complex number we have on either side is 0. 0 is a real number, and of course real numbers are subsets of the complex numbers. So what I've done here is meaningful. Now we can then go and use the fact that we have sums of complex numbers here to split up this conjugate. We can get the conjugate of 1 plus 2i squared, followed by minus 2 times the conjugate of 1 plus 2i. Then we can get the conjugate of 5, and that equals the conjugate of 0. So this was one of the properties I proved in the previous video. If we have several complex numbers added together, we can, to get the conjugate of them, we can just get the conjugate of each number separately. We also show that if we have the conjugate of a number squared, it's just the same as the conjugate of the complex number all squared. That was another property that was proven. That was the multiplication property. Now we can take minus 2 out of this. Actually, the conjugate of 1 plus 2i, as we know, is 1 minus 2i. Now what is the conjugate of 5? Well, the conjugate of a real number is just that number. We can think of 5 as 5 plus 0i. So its conjugate is 5 minus 0i. But of course that's just the same as 5. Similarly here, 0 is a real number, so its conjugate is just itself. So finally we get the conjugate of 1 plus 2i here, which we know is 1 minus 2i. So we get this equation here. But this is the same as our quadratic equation with z replaced by 1 minus 2i. So our original quadratic equation is z squared minus 2z plus 5 equals 0. If we replace z with 1 minus 2i, we get this. But look, all of this equals 0. So that tells us that 1 minus 2i must be a root of the equation. 1 minus 2i is a root, because when it's plugged in for z we get 0. So this is a proof that the conjugate of the complex number also satisfies the equation. Now this is a result that we're going to use a good bit. Now here's a statement of the conjugate roots theorem. So if z is a root of any polynomial equation, it doesn't matter what the degree is. The degree of this equation is n. So I'm assuming here, by the way, that n is some natural number, so we're only going to take this case. Then the conjugate of z bar is also a root. So the highest power is n. Now n could be 2, it could be 3, it could be 4, it could be any power, and the a's are just numbers in front of the z terms. So for example, if n equals 3, then the first term would be a1 z cubed. The second term would be a2 times z to the power of 3 minus 1 z squared. The next term would be a3 times a2 z squared plus a3 times z, and the last term we could call it a4. Okay, this here is a cubic equation. The highest power is 3. By the way, this should be n plus 1 here. We actually have n plus 1 terms if the highest power is n. So if the highest power is 3, if we have a cubic, we have 4 terms in general. Of course, any one of these terms could be 0. We could have set this to 0 and then it goes out, or this to 0, or this to 0. But if we want to have a cubic, this a1 cannot be 0. So anyway, here's a quick proof. You can ignore this, of course, but it's just like the way we showed this result for the quadratic equation. We get the conjugate of both sides. We know that z satisfies this equation, so we are assuming that z has been plugged in here, and of course we get 0. Now we take the conjugate of both sides, and then we use the properties proven in the last video to rewrite this like this. The conjugate of a sum of complex numbers is the sum of the conjugates. So each of these is a complex. This is a complex number when we work it out, because z is a complex number. So we can take the conjugate over each term in this sum. Now I'm assuming here that all the a's are real numbers. ai are elements of R. So ai stands for any of these coefficients, a1 up to an plus 1. Okay, so that's just a property, and then we can apply the other property, which says that the conjugate of a product is the product of the conjugates. So we can write this term like this, but the conjugate of a1 is just a1, since a1 is a real number. And then we have the, actually I should have shown this, we just take the conjugate over each term in the product. And this is similar. We have the conjugate of a2 times the conjugate of z to the power of n minus 1. But the conjugate of a2 is just a2, since a2 is a real number. And since we're an plus 1 is a real number, its conjugate is just itself. The conjugate of 0 is 0. Finally, we use the other property about the conjugate of z to the power of n equals the conjugate of z to the power of n. But you see now that this here is the same as the original equation, with z replaced by z bar. So here's the equation, and if you replace z by z bar, you'll get this equation here, and you see that it will all work out to 0. So that tells us that z bar is a root of this equation, is a root of this equation here.